Hello, everybody. Welcome to another Dante webinar. As usual, we're going to give it a couple minutes to let people get in, and we'll probably start a minute or two after the hour. Okay, we can get started here. Anybody who comes in a little bit later can catch it on the YouTube. So welcome again to another Dante webinar video here. Today we're going to be talking about low pressure carburization and how to model from process design to the full Ansys model. This is going to be a little bit more of kind of like a workshop where I'm going to show how to actually set up the carburization model in Ansys after we develop a model in VCarb. So a little bit on the outline here today. We're going to have a little bit of an introduction to Dante itself, like the company and the people here who work with us. And then we have a little bit on Dante modeling as far as some of our models and how we go about modeling the heat treatment process. Then we're going to do a little bit of a low pressure carburization basics, and it's going to talk a little bit about how the boost and diffuse steps work and concerns for that. And then we're going to design a quick schedule using our VCarb software for 5120, targeting about a millimeter case depth in the flank of a gear geometry that we have. We're going to export that schedule, and then we're going to bring it directly into Ansys, a carburization model, and we're going to show about setting up those models. We're going to include some thoughts on meshing for a little 3-tooth gear section that we've developed. We're going to import that schedule that we developed in VCarb, and then we're going to show about exporting the carbon profile from the carburization model after we've modeled the process. And then we're going to use that carbon profile in a thermal and stress model to show like the development of the heat treatment modeling process. From the thermal model, we will show some results for phases that are developed, and then some hardness results. And then the stress model will show distortion and some residual stress that we have developed. A little bit on Dante Solutions. Dante is an acronym that stands for Distortion Analysis for Thermal Engineering. We were founded in '82 as a company called Deformation Control Technologies. And we were mainly focusing on modeling of thermal processing of metals at that time. During the 1990s, we were part of a large collaborative effort between industry, academia, and the national labs to predict distortion in heat-treated steel alloys. And that was out of the need to reduce scrap and costs in those industries. So out of that effort, the Dante software was born, and ever since 2000, we've been updating it and developing, adding more models, and really making validations as much as we can throughout the years. Our main line of business are Dante software licensing. We also do some heat treatment technology development, and then we do consulting services with our product. You can see some of the guys here. We're actually missing one guy here, but it's basically 7 guys in Cleveland, Ohio, just really close to the airport, just south of Lake Erie. So a little bit on heat treatment process modeling itself. There's a lot that goes into heat treatment process modeling. You can see a little bit of a dialtometry curve here. So those who are familiar with it understand the triangle here. This is well represented. Basically, when you have heat transfer, you have thermal expansion, and you can see this through this dialtometry curve. As the temperature increases, the strain also increases, and the volume gets bigger, like the part gets bigger when it heats up. At some point with steels, there is a transformation to austenite here, shown by the AC1, and that is the temperature-induced transformation here. And that has a volume shrinkage because it's a little more dense than any of the other phases. And so when it shrinks, you see a little bit of a shrinkage here, and then upon cooling, we also have a thermal shrinkage. And then there's a transformation somewhere along the line, depending on how fast you cool. For this example, it is showing Martensite transformation, and there's a volume expansion from that transformation. And when that volume expansion happens, that volume change, you get a little bit of a deformation, a change in volume, a change in shape or size. And that is due to the change in crystal structure from the FCC to the BCT structure here for Martensite. We cover thermal expansion. There's also latent heat. So when these transform, when austenite transform, it actually absorb heat. So we have to calculate that. Most of the time during the heating process, that's already accounted for. And then during cooling, there's also a latent heat of transformation from austenite to martensite, and that actually releases a little bit of heat. So we can calculate those into the heat transfer model, and that's what makes our process a lot nonlinear to model. That's why we use all of our models that we have. So in order to model all this, we have to use phase transformation models, multi-phase mechanical models to account for all those different phases. Most people know the mechanical properties of austenite are very different than that from martensite. So we have to have a model for each of those as well. We used trip and mixture laws as well. We need tempering models to model the softening of martensite, but still having a little bit of strength there when you temper. We developed a carbon partitioning model in recent years, whereas if you have a phase transformation, some of that carbon can go back into austenite and enrich that austenite, reducing the local martensite start temperature of that austenite. So we have the models for that were developed. We also have carburization models, which again we're going to use today, which doesn't just include diffusion, but also some carbide formation and dissolution, which adds a little bit of nonlinearity to the process. And then we also have the nitriding models, again, not just diffusion, but also white layer formation and precipitate formation from those nitridings. And all that kind of goes into a heat treatment process that we develop. So when you get the Dante software, we kind of see the little process tree or a little structure tree here. The installation directory for Dante includes your license and equipment. It also includes a user database that you can use to develop your own materials or to modify the existing materials in the Dante. And then the actual version includes all the information for Abacus and Ansys that we would need for the libraries and plugins. And they also each include examples, tutorials, install tests, and everything to really get you started in producing good heat treatment models. It also includes our robust standard database and some control files and our utility tools. Now, our utility tools are kind of little snippets of the full FEA Dante code. Today, we're going to be using the VCarb software to develop a boost and diffuse schedule. You can kind of see one here that was developed for the carburization process. But we also have ones for material simulator where you can see the time temperature history and see what kind of results as far as hardness and phases that you would get. Some fitting tools like heat transfer coefficient fitting tools or mechanical or phase transformation kinetic fitting tools, as well as a couple other niche tools that we use. So those all come with the database here, and that's what that includes. So for the material database, like I said, there's a lot of information that goes into the heat treatment modeling process, significant amount of material data. So we have like folders here that each has each one of those files that denotes whether it's the mechanical file or the phase transformation file are each in one of these. So in our standard database, we have about a little over 70, almost 80 standard material grades inside of them. And you'll notice some of these materials here have like XX next to the name. So for this one example, 41XX, it's a carburization grade. So we would have carbon measurements, carbon data for 4120, 4140, 4160, and on up to make sure we capture that carbon gradient and the effects that carbon has on the material steel. So like I said, they include the phase transformation kinetics in these the folders as well, along with the plasticity model. Mechanical properties are in these. We also have thermal stuff like coefficient of thermal expansion and transformational strains. And we have hardness related properties, include individual phases and carbon and carbides, coarsening rates and stuff like that, depending on the material. And all of these have been like validated through experiments over the years that we've been working with these. And then we continue to update to make sure the validity of the models hasn't changed anything and to make sure that they're still valid. Again, I mentioned a little bit, but we can also develop your own proprietary data through some of the help of the utility tools like the fitting tools I talked about. And then this would be something that the user can customize. You can modify an existing one to be a little closer to what your individual melt or chemistry is, or you can develop new materials through here that you can use it at your own discretion, and Dante doesn't control. So that's a little bit on the Dante software. Here's some of the parts that we modeled. We do long induction shafts that show the transformation along the length of the shaft here. This is a pretty good example. You can find that on our website. And then we have a lot of gears. Like most of our work is gears. We have regular spur gears, or even bevel gears, or even like geared shafts that we've modeled in the past with great success here. And then also landing gears, not technically a gear, but it still follows the process. And this is a little more challenging because it's such a large part, and the immersion process is very important to model correctly in order to get the bow distortion that is usually significant for those type of materials. Today we're going to do something similar to this, a spur gear geometry that I found on McMaster car. So we can do something similar to this, where we're going to carburize the gear teeth, and we'll go from there. So a little bit of an introduction into LPC. Low pressure carburization is a carburization process that uses a series of boost and diffuse steps. You can see in the blue steps here, we're a boost up to a carbon potential near the surface, and then it allows a time for a diffuse to diffuse into the part. And then it was repeated over and over again until you meet your case depth and your surface carbon requirements. So during the boost steps, that carrier when carrying gas quickly goes to saturation at the very surface, and then it's allowed to diffuse into the part at that point. And then so we also take into account for carbide formation. The example today will just be a simple boost and diffuse with 5120 here, but if we boost too hard, we can form carbides. And this is really the most important part about the LPC process, and actually fine-tuning it to make sure it's the way you like it, because these carbides that form at the very near surface are additional carbon sources. So if you don't model them, you'll probably have you'll predict a shallower case than what you would actually get in real process. And a lot of LPC is really controlling these carbides and making sure that you don't have to worry about them in the final product when you're done here. Here's some examples, a little bit of a spur gear as well here, which shows a little bit of carbon, more on the tips here, and the predicted carbon distribution overall. You can see it's a gradient as it goes through the part here. There are going to be more carbon on the edges, and that's because there's diffusion from the tip of the tooth as well as from the outside edge flank, and that double up kind of gives you extra carbon, and that could be also where you would find carbides in your process, or after your process, you might find some carbides around these tips because of the geometry. So here I have a little bit of animation. A lot of these animations are things that were on our LinkedIn as far as Animation Fridays that we just kind of show off our capabilities. So this one I'm going to start really slow. This is just a simple spur gear with a LPC process applied to it. There is a series of boost and diffuse steps. So we're going to start right at the beginning here. We can see on the left contour here the boost step with the carbon, and on the right we have the carbides that would be formed during the process. As far as I remember, this was a very high alloy steel, so we do form a lot of carbides as it was being processed. And I believe it was meant to be an aggressive process to show these. So as we go through the boost step, the initial boost step, you can see that carbon is being delivered to the surface, and it quickly reaches carbon saturation levels for that material. And I'll stop right here. This is at the end of the boost step here. You can see that we have about 1.5 or so carbon weight fraction for carbon at the surface here, and it is starting to diffuse very slightly into the part. You can see by the little green contours here. And then also for the carbides, we can see we formed a bunch of small carbides at the surface here, which when we start to diffuse, you can see them start to go away during the diffuse step. And then you can see the surface carbon also kind of goes down a little bit because that carbon is diffusing into the actual gear surface. And then so the rest of the process here repeats this over and over again. You can see the boost and the diffuse, boost and the diffuse, until we finally get to the end of the step here. And you can see the total carbon plots. You can see that we diffused very well into the actual part surface. And then we can see there are showing a little bit of carbides here on the flank or in the tip of the tooth interface here, but mainly they're very little or almost all gone on the flank here. So a little bit about the VCarb software. We developed this software tool to predict the carbon profile and then any carbides that may be present. It was developed for both low alloy and high alloy steels. So if you are running a low alloy steel, you probably will not have the carbon formation, but it'll still be able to predict and design recipes for those alloys without the carbide formation. So the high alloy steels really need to manage the carbide issues. You can see we have a, oops, that didn't work. Go back to, there we go. Okay, so you see we have a little bit of a contour here. I was going to try to expand it, but I am in presenter mode, so I can't edit while I'm working. So you can see there is a large form in carbides with this process, and then there's a lot of network carbides. So this is kind of a very bad situation that you try to avoid. But when we plug that recipe that we used into the VCarb software, we can see that this dotted line here is those carbides that we can see to the 0.132 or so millimeters depth. Hopefully you guys can see that as well as I can. And then the other predicted carbon profile is through here, the case. So we really want to kind of manage and reduce the amount of carbides that are formed, especially with these high alloy steels. So we use that carbide decomposition models that we developed during the diffuse steps, and that'll help control the carbide case and then the actual amount of carbon that's going into the process. Like I said, they act as kind of extra sources for carbon than just the surface, because as they dissolve, they add more carbon to the process. So we like to predict, like a lot of these predictions that we developed here aren't just math, so they are validated with real life experiments, and we like to use legal burn tests to kind of validate the carbon profile based on depth, where they machine off a little bit and then they burn that, and that carbon that comes off of it is used to know how much carbon was at that depth. So we have a bunch of demonstrations on VCarb already on our website and on our YouTube. We've had a couple to use Dante VCarb to design like the schedules for boost and diffuse, and then we looked at shallower case and deeper cases, and then the amount of carbides at different depths. We have one example on that. We also have the effective steel grade on carburizing results, so we can change the material and see with the existing process to see if that process will still be good for the new material using the same schedule. We did some work on geometry effect on carburizing, so like the gear and the root flank difference. So when you work with a gear, you have the flank, which is relatively flat and maybe a little more convex surface, and the root is a very fine concave surface. And so the way the carbon is profile is developed for those, you will get a difference between the root and the flank difference. Usually the root is a lot less carbon compared to the flank. We have examples on that on our YouTube and our website as well. And then we also have the exporting the LPC schedule from design features and importing into a prediction feature. So with VCarb, we can design a schedule based on surface requirements and case step requirements. And then we could also export that and bring that back in to modify or design that schedule to whatever needs we would have. So there's an example of that as well. And then there's recipe fine tuning for specific equipment. Some equipment is a little better at delivering carbon to the surface, and some is a little worse. And just by knowing your equipment, you really need to fine tune that a little bit if you want to get a really good accuracy. Today, we're going to design the schedule using and use it in the full FEA for the carburization model. So what we're going to do here is we're going to open up VCarb. We have design and export. We will use our material 5120. We will use a 1 millimeter required case depth and then 0.8 surface carbon. And you can kind of all see those process in the process design tab here. We're going to design it for this this spur gear that I found, like I said earlier, online, and we're going to use a 3/2 section when we actually model this, so we don't have to model the whole thing. To be honest, we probably could have used one, but I think 3 looked a little bit better when I set up the animation for this. So the gear here uses a radius here, outer radius on the flank. Like I said, it's usually a convex shape here. of about 6.23 millimeters. So we'll use that when we actually design the process as an outer radius, and that way we can make sure that we hit the K steps and stuff that we're looking for. So with that, I will pop up Dante VCarb here. So this is already set up, ready to go. This is basically when you open up VCarb, this is the blank slate that you have. And we have a bunch of different options. We have prediction and process design. Prediction is you can start your own process. You can plug it directly in, and it'll predict the carbon profile and service the whole carbon profile. We're going to use process design first, and that way we can design a schedule based on our requirements. For the material, we were going to use 5120. So we have 51XX is the name of the material that we use. And then the base carbon content, we're going to use 0.2 for 5120. You can change your nominal and modified grain size. So the nominal is basically what we've tested. And then anything that you would want to change would be on the right-hand side here. So if you wanted to change the grain size, you can do that as well. Or if you have a specific chemistry that's a little bit different than what we tested, you can adjust it. You have to adjust it within the range of 5120 or whatever respective material. So you can't make it like 5180 or something like that to adjust the different contents here. You can't make a new grade. So it works that way. So then we follow through the process here. We can go to the geometry. And we, like I said, we have an outer radius, and it was about 6.23 millimeters. Let's go 6.24 because we can round. And then so this sets up the part radius for the outer radius, and this will give us the diffusion through that kind of radius for the carbon profile. We also include a load surface area. So this is used to calculate the amount of carbon carrying gas that's used up by the part itself. So this doesn't really affect the analysis in any way, but after the analysis, you could look at how much carbon carrying gas was absorbed into that part of surface area. And then last, we have model thickness, and this is basically just how deep to run the model. This is modeling parameter. You can 5 millimeters would be just fine for what we're using, since we're looking for about a millimeter case. You want it to be beyond the actual total carbon penetration depth. So with a 1 millimeter case, maybe we go to 2 millimeters for carbon. Okay, so now we're onto the process tab here. We have several different processes or different levers we can pull here. Starting with the top, we have the furnace roundup time, and this is basically for the modeling. It's every a lot of times when you set up recipes, it depends on the control of the system. Sometimes you can't control it to the exact second. Sometimes it has to be every 5 seconds, or sometimes it has to be every minute or so, depending on your furnace. So we can adjust this through this value here, and it's basically the simulation will go every 5 seconds. It's kind of a time step here. We do have carburization temperature. 925 is good enough for the process we're working today. But you can change this obviously for faster or lower, and you can look at the effects on a higher temperature. If it saves a lot of time, it may be a better way to go without losing grain size. Next, we have the gas partial pressure, and this is the carbon carrying gas partial pressure. This is how much carbon carrying gas can go into the system. We have an effective K step that we would look for. We're looking for 1 millimeter, so we can leave this one just blank. We have the carbon percent at the carbon K step. So different materials have different hardness values for different carbon percentages. For 5120, the 0.35 to 0.4 is pretty good for us. So we're going to leave that as the default here. But if we have a higher alloy steel, we may need less carbon to hit that 50 HRC that we're looking for. And since VCarb is just a carbon diffusion software, it doesn't know the hardness. So it has to go, we have to go by carbon percentage. Next, we have a monitor point, and this is basically how we run our analysis here. We have a depth, it's slightly below the surface of 0.02 millimeters here, or 20 microns. And that point is when we do the boost steps, we boost up to a certain bound. And then when we do a diffuse step, we make sure that point gets down to that lower bound. And then those upper and lower bounds can be modified through here. I'm going to go ahead and change this to 1.2 for this and be a little more aggressive for our process. And then I'm going to leave the lower bound to boost down to 2.7. So the surface will actually be a little bit higher than 1.2 during the boost. And then as it goes down, it'll also be a little bit higher than the 0.7 because it's at however many millimeters away you define. And then finally, the surface carbon, we're looking for about 0.8. That should be good to get us about 60 HRC or so for 5120. So we're going to leave that as it is. Finally, we have the controls tab here. We can set it for degrees Fahrenheit or Celsius. Dante uses a little bit of modified SI units here where it's millimeters instead of meters, but everything else is seconds, Celsius, and so forth. So if you do use American units or English units, you can go ahead and change these here. And we also have them for flow rate as well. We have a furnace reaction factor and a carburizing efficiency. So these are more of the tuning, like I was talking about, how if you have a furnace that has a little slower to build up the carbon value, you can adjust these to get it a little closer to what your furnace actually does. And then finally, we can set the Dante material directory and then where to find the carbon saturation determination. And right now we're using the Dante material database for that. So that's all set. We can go ahead and click Analyze here. And I'm going to go to my temp directory and go ahead and overwrite the tests I was doing earlier. And we can plot that. And we can see the case steps that is predicted here. This is for the last step under the settings menu. We can actually look at all the different steps. And we can update the plot. We can see during the boost steps, we boost up to 1.3, which is the saturation level here for this material at this temperature. And then we can see the diffuse steps, we get down to about 0.7 that we were looking for. And then the final profile is this green line. We can see if we go back to settings, uncheck everything, and just show the final process. Okay, so we see we get pretty close to the 0.8 here. We're a little bit deeper than the 0.35 than the 1 millimeter here. And then we can always bring this out and adjust the schedule. If we look at the results section here, we can see the actual boost and diffuse, the process times. This one's set up a 16-step process or 8 boost and diffuse pairs at that temperature. And then here's the actual times for each one of those steps. And the total furnace time is about 23,000 or so seconds. The boost time is about 1,700 seconds. And so we have an R value of almost 12 here. So we develop a schedule. We like it. We're going to go with it. We're going to model it. So we can go to our boost and diffuse schedule here, and we can look at the schedule here in a more of a tabular format. We can see here, we see the settling flow that was calculated based on that boost time and the partial pressure. That's how much, and the surface area, I'm sorry. That shows how much settling flow in liters per second that we would need just to absorb into that part. So from here, we can make some changes, but I'm going to go ahead and export the file here to a predefined text file here, and we can save this schedule to a text file. All right. Then from there, we can also, just to show the functionality here, we can go back to the prediction tab, and then we can load data in here, and we can load data from that text file. If we wanted to, we can go ahead and adjust these parameters. Let's say we wanted the boost to be, the final diffuse to be a little bit shallower. We can always adjust this, and then we can see the changes that would happen. You can see a little shorter time, has a little less diffusion, and it increases the surface carbon a little bit, but it doesn't really affect the case step as much because it's the final diffuse process. So we're going to leave those as they are. I am going to start Excel and open up that text file to show what we've created. We will open up the blank workbook, and we will open that text file in my temp directory. Oops, wrong one. There we go. Files. The temp text file. Okay. So we can open this up. This is a comma separated values. So we can go ahead and delimit by commas here, and we can see that here's the output of the text file that VCarb generates. We can see here we have the step times or step numbers and then the step times. For modeling the process, we do need to have these step times as total time. So what we can do is we can copy the first step over here. I created inserted a line, and we can say that this cell equals this cell plus this cell. And what that does is it adds everything up here, and we can add it through the process. And now we have total time. I'm going to go ahead and copy this because we're going to be using that here just in a second. Okay, and then back to the presentation here. So now we have designed our schedule. We can now use this schedule to do the full FEA process on this gear. We can see we have the full gear geometry. We imported the step file that we got from McMasterCar, and then we simplified this down to a 3-tooth model. Basically, we were able to slice based on the degree these 3 teeth out here, and you can see that this is the model that we're using. So a little bit, the first thing that we would do here is look at the workbench. So this shows Ansys workbench. This shows our general process flow that we use when we do heat treatment models. A lot of times we have a geometry, we bring it in, and then we mesh the geometry. And then that geometry is imported into a carburization model. And then the next step would be a thermal model or a stress model. When I set this one up, I was testing the functionality of having a different mesh for the carburization and the heat treat. So we have 2 different geometries for those models here. If I'm going to go into the model thing, I can show you a little bit about the meshing. Give that a moment to open up. And so meshing is kind of an art form. You really have to think about what you want to get out of the model. For LPC, you really need very fine elements at the surface of the part because the temperature of the carbon gradient is very high. So we have I set up a little bit of a model for mesh considerations here a little while ago to see the differences between a fine mesh of about 20 microns for LPC or coarse mesh at like 200 microns, which is common for gas carburizing and stuff like that. Because of that saturation level is so fine on the surface, there is actually a very huge difference between the meshing. So you want to make sure that your mesh is fine enough to capture that gradient. For heat transfer, you need a little bit less, but because of this is so high. You can see I got carbon on the top and then carbide at the bottom here. On this side, we have the fine mesh, and then on this side, we have the coarse mesh. And the difference between the boost and diffuse schedule becomes pretty apparent as the carbon is brought across the element, the larger elements there. It actually goes to a deeper depth because it's just basically averaged across that depth of the element. The larger the element you have, the more it's averaged, deeper it goes. You can see at 0.4 millimeters below the surface, I have a little bit of a graph here that shows the time. And we can see it starts out very small, the difference here. But as we go through the boost and diffuse process, we have about 0.2% more carbon at that depth of that 0.4 millimeter depth in the coarse model than we do with the fine mesh model. Same thing with the actual case depth. We can see that the case depth here is actually a deeper case because the larger elements were averaging it more and more over through the process. So that is mesh considerations. So for the mesh model, which should have opened our mesh geometry, there we go. All right, so we have the Carb mesh geometry file here. We can see, let me just click on mesh. You can see that I have a very fine mesh here on the surfaces here. So what we like to use a CFD physics reference here for when we develop these, because it has the advantage of having an inflation layer. Here for this, I used 11 layers with a total thickness of 1.2 millimeters. And then there's a little bit of a growth rate where the surface element is very small compared to, and then it grows from there about 1.2 times each. And if we kind of zoom in on that element, we can see that that is within the range of about the 0.2 millimeters. We have to go really far in to see it. And then it gets bigger as it goes through. And this will help capture the steep gradient and make sure that we're pretty accurate as far as that process. And like I said, the mesh is kind of an art form. I like this mesh, but I think it could be improved. A little bit about the roots here. You can see it didn't capture the curvature as well as I would like it to, but we can always adjust that later. And then also on the edges here, the elements are a little bit long, these kind of wedge elements, and we can change those with different sizings. Here I used a face sizing and another face sizing here on the tip of the tooth in order to pack the elements in that direction. This process is going to use a selective carburization process, so it'll go in from the surface, and it'll have just basically the flank surfaces and roots all carburized here. I have that set up as a name selection here. You can see that will be the carburization surface here. think I have a few seconds. I could show you how we could set up those name selections. Basically, we would just choose our face selection here. And then when we go in, we can select all of these pretty easily. And then we can remove the sections that we don't want. And then we can see that this is kind of basically the same selection that we just had. There is a few I missed. There we go. And then from there, you would right click and then create a name selection. And then you can now have a defined surface. And that surface uses or is used in the inflation surface here. So we can choose all faces of the chosen name, and toSurf was the name of that surf that was set up. And then that's where it uses the inflation layer into the part. And that might be a little bit, you can see also that we have some pretty chunky elements here in the core here, and those are just fine because with the carburization model, we're only focusing on the carbon region, and carbon doesn't penetrate down to here. Okay, so I can go ahead and close that, and I'll go back to the modeling here. This kind of illustrates a little bit what we just talked about with the different options that we have. This model uses about 151,000 elements, just for your reference. Okay, so now we can do the carburization model setup. What we're going to do is we're going to set the number of steps. We're going to paste the recipe times. We're going to adjust some min-max as far as time stepping. And then we're going to make sure we use nonlinear formulation to full. And that is so that we can use our Dante material for the nonlinear formulation. We're then going to set up a convection boundary condition that'll actually model the boost and diffuse steps that we have. And that basically uses convection as the concentration of carbon. And then we're going to talk a little bit about the Dante ACT and how we developed it, and then basically step through the process for that. So I'm going to go back to our workbench. We can see we already have this model set up, but I'm going to go ahead and start a new one here. I'm going to drop this into, this is a transient thermal analysis. So we're going to drop that directly under the one we just ran, and then I'm going to link the mesh model that we have to that carburization model. Okay, and then we're going to go ahead and double click to open up the mechanical. Now, this usually slows a little bit down because of Teams, so we'll give it a moment, and it will be ready for us. We're looking good on time here. Okay. That's loading the project. Give it a second. Okay, we're loaded here. So we see we have our geometry here. If we go to click on mesh, we can see we have our mesh imported properly from the mechanical model. So the next thing we need to do is go to the initial temperature. We're basically going to work down here. We're going to change this to 20 degrees C, so that, starting at room temperature. And then for the analysis settings, this is where we define our steps and our step numbers and everything. We have our step times. We can just paste these in here directly from the Excel that we had. And that'll bring up to 23,120. Okay, so that is our full process time. I'm going to copy that because I will need that later. So this set up our 16-step boost and diffuse process here just by pasting them directly in from that Excel document that we set up. I'm going to select all the steps here and right-click and highlight these steps so that they're all as one. You can see that the step number has changed to multi-step. And I'm going to go ahead and set up a little bit of controls that we have. I'm going to set auto time stepping. We like to start with an initial time step of 0.01 seconds, but we also like to give it a little bit of extra 1 e to the -5 or 1 e to the -6 as far as the minimum time step that it can take. If it tries to do a time step smaller than that, the analysis will stop. And then, so the maximum time step, I typically use the value for the shortest diffuse step. So we can use this 175 seconds for that. That way we don't skip over or anything. And it allows the analysis, if nothing is really changing as much, it can take that much time step. Spoiler, it won't. And then, so lastly, like I said, during the nonlinear controls, we must use nonlinear formulation to full in order to use the Dante materials. And then the last thing, as far as just the Ansys section goes, is we have to apply the convection. And then we have to apply the convection to the geometry selection. We're going to use the name selection that we set up, and we're going to use that tooth surface. You can see that turn yellow here, and that shows the teeth that are going to be carburized. We're assuming everything else is copper plated or something similar to that. Last two things we have to define are the film coefficient and the ambient temperature. The film coefficient here is basically how fast it can deliver carbon to the surface of the part, much like for heating, how fast the heat can be pulled away or so for the part. So we're going to use about 5,000 watts per meter, if you guys are familiar with those. But the Dante database uses millimeters, so we have to use 5e to the -3 in order to use that. And then for the ambient temperature, we would use the carbon saturation value. For this material at this temperature, it's about 1.3 for that, and 1.3 e to the -2, I'm sorry, percent. There we go. And we can see that that's tabulated into our table here. We're just using constants for this example. Now, if we were to run this like this, it would basically keep the same coefficient and temperature the whole way through. We can't do that because we need to have boost and diffuse steps. So step 1 is a boost, step 2 is diffuse. So we choose all even steps. We can highlight all the even steps, 6, 8, 10, 12, 14, 16. And we can right click and activate, deactivate this step. So basically this deactivates the convection on that surface during the diffuse step, allowing the carbon to go into the process. And then that's it for the Ansys controls. Now we can go into the Dante toolbar here. If you select this and go to carburization model, we can see that it populates with these green buttons here. There's a little bit of a line here, and everything to the left of the line is pre-processing, and everything to the left, the right of the line here is post-processing. So for setting up Dante here, we basically work left to right here. We're going to choose material. And then when we select material, we're going to choose the geometry and say the whole material is the one material. You can also do partition sections if you do have other materials or welding options or something like that. We can handle, I believe, up to 5 materials in one analysis. Next, we're going to choose the material name. So again, we're going to choose the S51. Oops, 51, and we got that right there. So those are 5120 series. You can see the 0.2 carbon percent here. So that's ready to go. Next, we have to set up our carburization temperature. And we set this up by a time temperature chart. You can adjust the carburization depending on if you have step downs in your process. For us, we're just going to use the 23,120 as our end step time. And then for this temperature, we are going to run 925 because that's what we designed. A little bit of a cart before the horse. When I ran the models, I actually ran it at 950. So make sure that you set these proper. I ended up getting a little deeper K-step than what I was planning when I ran the models. Setting the step time here is 925 constant the entire time. Next, we go to our model controls. And for carburization process, there isn't very many controls. Basically, it's the max carbon change per substep. So when they solve the substep, if the carbon changes by 0.05% or more than that, it'll ask for a cutback, and so that we can make sure we capture the whole process properly. The other one is for the material directory. If you have a different material directory, you can always assign that here. Next, we have the output frequency. So this depends on how often you want to see results. For this, we really are only concerned with the last step of each step. And to be honest, when we're looking for the carbon profile, we're looking to look at just that last step here so that we can use that in other models. So 10 is just fine. If we want better resolution, that does increase process time. We can set this down to 2, which means every second increment is shown. But for this, every 10th increment is shown, and it's usually the last step for that process. And that is it. We would just finalize the material model here, and then we can right-click on the solution and solve. I'm not going to do that right now because this takes about an hour to do, and I value your time. So I'm going to go ahead and close that, and I do have the carburization model workbench already set up here. So we can see, here that we have the solution, the same solution that we have here. We see boost and diffuse steps here with the maximum and minimum and average carbon here, but we can see this on the actual plot here. And this is the carbon that was achieved. We can see we're just below 8% or 0.8% here on the flank surface that we designed for. And then the root is a little bit less. You can see this is probably closer to about 0.7 or 2 or so. The gradient is a little bit misleading because these values are very small, but it does show different colors for those. You can see the solution took about an hour to run, hour in 2 minutes, 12 minutes or so on my system with 4 cores that we have here. So we can see also a little bit of a post-processing here. We can do path plots. This one shows the path plot for the root, and you can see the direction through the root here. And then we also have the one for the flank on the curved surface here that goes through. And then we also have one for the tooth flat, the flat portion near the end of the tip. And this is interesting because we have carbon coming in from both directions, and this raises the core carbon value for that path in that local location. So that model ran pretty well. We can actually show an animation of the entire thing. We'll say over 10 seconds here, and you can kind of see it disappear completely. No, I'm just kidding. So you can see as it boosts the surface carbon, and you can see the diffusion happening during the diffuse step as it goes through the part here. So this is really good to see. You can really see what's happening at the end of each one of your boost and diffuse steps. Make sure you're controlling any carbides that are forming. Again, for our example here, we don't have those, so we don't need to worry about them very much. Okay, so that is the carburization model. So once we have this carbon profile, we can use it for all sorts of things. We have a little dialog here in the Dante carburization dialog here to write the carbon profile. We save this to our Ansys directory in a little folder called Dante files. And it's basically a nodal value for each one of the carbon points here. And then so once we have that carbon profile, we can use it in different models here. We have a thermal model here, which basically shows a heat up, a transfer, a quench process, a little bit of an air cool, and then a tempering process for this gear here. And when we bring that in, we use our Dante, again, toolbar here, and we bring that in as our CN profile. So if we look at the CN profile here, we can see that it has a path to where I was running this file to that 5120 1 millimeter case depth carbon file that we've just created. And then we set tabular data, which will set when we apply this. I have this being applied to the transfer step just before quench, so we can make sure we have that carbon going into quench here. And then from there, a thermal model requires some extra work, a little bit about convections as far as the heat up, transfers, and quenches, each one only for their own step. And it does include a temper process here. So for the solution for that, we do have temperature history. We can see that through the graph that I just showed at the bottom here. We have austenite volume fraction. We can see during heat up, we form austenite, and then during quench, that austenite gets decomposed into martensite. There is a little bit of residual retained austenite here, and then that goes away a little bit after temper, but then at the end of the process, we're predicting about maybe 6 or 7% on the root flank here. We also show ferrite volume fraction, so this is a little bit of ferrite here in the core here, only about 16% or so. We show a little bit less perlite, get a little less carbon for that. So we have a little bit less comparatively. A little bit of upper bainite and lower bainite was formed here, but very trace values. A little bit more in the core here for the lower bainite as it cools a little bit slower than the rest of the process. We can see martensite volume fraction as well. And the martensite here is showing only about 7 or 8%, and this is because during the temper step, it's decomposing to tempered martensite, which we show contour here. And you can see it's about 97% around, and then where the carbon was high, the balance is the rest is retained austenite that we saw in that graph here. And then finally, we also output total hardness. So we can see the hardness. You can see we achieved about 60, 61 HRC here on the flank, and then a little bit less as it goes through the gradient of the part. Core properties are about 32 HRC. So that's a thermal model. It'll show you the phase transformations and the hardness values. That's really useful. But we also use that thermal model to drive the stress model. If it'll let me click it. There we go. And then this is the stress model. You can see, again, same gear here. We can see some, I have maximum principal stresses shown right now. And we can see the surface is relatively neutral. maybe a little compressive here in the roots because of the geometries effect there. But what we really want to see here is there's a level of tension that we can't see on the surface. We can go to the home directory here and go to a section plane and apply a section to this so we can cut the tooth and actually see what's inside. From here, we can see the compressive stresses under the root from the volume expansion. It's just kind of a geometry. You got two angles pushing together, so it kind of creates a little bit more compression here. And then under the carbon case, we can also see the tension that's formed from the compression. You always have to have a balance. And we can also animate this and show um, the process as it happens. And we can see that during the Martensite transformation, that's when the tensile region starts to form here. Apparently, this is a little bit advanced right now for Teams and my systems. It's having a hard time running for the stresses as well. We can also do deformation. Oh, here we go. We can see the Martensite transformation there. And then in a few seconds, it'll even out. Again, we can also look at deformation. We can look at total deformation, where it shows like how the whole thing grows. We can also look at deformation in a certain axis. This one being a two slice, I was able to use a cylindrical coordinate system for that. And really like to show it to you, but I accidentally hit the animation button here. So we'll let that kind of go for a minute. And then we also have same things we have in the thermal model. We have temperature, we have hardness, and then we have all the phase transformations that you can plot in the stress model. So the stress model is kind of like the complete model that shows everything all together. From the stress model, you can export the stress that's there into loading models. So you can have a loading model that includes the tension under the surface and the compression in the root. You can do single tooth bending fatigue with these models as well, so that show a little bit of load to see how that changes your stress in the root. And you can also import these stresses into like full assembly models to see your power transmission and everything like that. That's goes with it. And I believe I'm running pretty close to the end of the time here. So let me just go ahead and go back to the slides here. We can see the thermal model results. And then, this is the one I didn't save. So we have the stress model results that I was showing here. Stress model is back up and running. Okay, we can see it's only 2 seconds here, but we kind of see it happen quickly. The Martensite transformation as the thing is being cooled, and then it grows a little bit. We can see this compression being formed under the root and the tension there. And then I could show the cylindrical coordinate system that we have here and show that the tooth kind of grows overall a little bit in this direction. And then this section here, due to the phase transformation, the shrinks just very slightly, maybe about 10 microns or so. So that shows that. And then again, the temperature history, total deformation. Yep. So that covered all of those things. So you can do a whole bunch of different stuff with this carbon profile that you developed. Hopefully the workflow here is something you guys can understand and found valuable here. Again, if you have any questions for us, you can always send us an email at support@Dante Solutions, or we have a lot of resources on our website as far as publications and case studies and stuff like that. Like I said in the beginning, that showed a lot of our low pressure carburization work. This is one of the technologies that we've really developed over the past several years to really capture properly. And that is the presentation. I want to thank you for your time. Hopefully everything was valuable to you. We do have a Q&A section here, but I do have a question. For LA grades not included in the Dante database, is there still a way to work with it? Yeah, so a lot of times we can use something that's close to the chemistry and the behavior of the material. And then if you have some TTD diagrams or dialtometry data or something like that, we can fine tune our parameters in order to fit that material to our database. A lot of times it depends on the material. If it's something brand new, it require a little bit more work. But if it's something pretty close to what we have, then you can adjust some of the parameters from there. Thank you for that question. And if anybody else has any other questions, we do have the Q&A. You will have to open it up and share your updates or ask a question. A little drop down next to your name. We have about maybe 5 minutes if you guys can use them. Hey, I think that's. See if there's any refresh real quick. See if there's any other comments or questions. Maybe give it another minute. Oh, new post. Here we go. Oh, thank you. You're welcome. Yeah, and if there's anything else that you guys would like to see as far as webinar, go ahead and send us an email at support@Dante Solutions. We love your ideas, and we really we're here to kind of support you guys. So anything that you'd like to see modeled or talked about, let us know. We can definitely set up a webinar for it. Oh, comment. Can you show a quick example of the hardness plot? You mean for the I had that in the thermal model for the gear section here, hopefully. It closed that one. Here we go. So the hardness is the plot that we had here. And we thank you, Eddie. And then we can go ahead and uh, do the same section plane that we had here. We can kind of see the two section here. You can set up a path geometry. I wonder if that's still in this. No, that's in the carburization model. But you can set up a path by right-clicking on the model, and you can insert construction geometry. And then in there is a path. And then the path you can define by 2 points I can do it on the global coordinate system. You can select a point to it that you want. You can look at that via the mesh here, and you can select a point and apply that to that one. And then for the second one, you can click the change, and this is just real quick down and dirty. You can apply that to that section, and well, that would not be a profile. You can also do the coordinate system as well here. So less y. So I can choose this 3, and then less y. Let's say 15. You can see the path kind of through the system here. And then when you were to evaluate the solution, you can go to the Dante database and then make sure we are on the thermal model. Go to the total hardness. And then in the scope here, we can choose a path, and the path is the path that we've defined here. I don't know why it says one node, but then from here we would right click and right. I might need to switch this node to a different node here for the path, but essentially that's the thing. And then you would just right click and evaluate all the results. And then it would show you the hardness values, kind of like how we did the carbon values. Oh, and in VCarb as well. I have VCarb here as well. So the settings in VCarb, we do have hardness, but this is assuming that it is 100% martensite in the case here. So we can see the hardness values if we had 100% martensite. So that means no retained austenite or any other diffusive phases. We can achieve 63 or so HRC on the surface. And then if we had 100% martensite all the way through to the 50 HRC, it would be about a 1.5 millimeter case depth. I hope that answered your question. Oh, okay. We had, do you have a list of the grades currently in the standard material database? I do have on that slide, but we don't have them like in full list format. But these are the ones that are in here, including all the carburization grades. there are a few more that have been added recently. If you'd like to have a particular one we'd like to talk about, you can just send me an email and we can make sure we have that in the database. Okay. I think that's the rest of the questions. Thank you again for your time. Looks like we are at exactly 1 hour. So if you have any questions or if you want to review this, we will have this uploaded to our YouTube here probably today or tomorrow at some time, depending on when Teams sends me the video. And again, thank you. Oh, I do have one more. Which kinetics of which way kinetics effects, especially on carbide precipitation and oscillate formation, are taken into account during the different steps LPC and oscillate through the time transformation stage? Does the software include additional precipitation diffusion kinetics in the models? Okay, that's a big one right here at the end. So we have which way the kinetics effects, especially in the carbide precipitation and austenite transformation. So this is basically the if you would activate the carbon partitioning or something in the thermal model, and when you're the effect on that austenitizing, that's handled through the Dante database here for the transformation. And the I don't think the carbon partitioning model includes the additional precipitation and diffusion through that way. What we could also do through the carbon model, if we have like a reheat or something like that, where the carbon would shift or move, we would model that at the end of the carburization process. So with the reheat, the time it takes to reheat and hold, we'll have additional diffusion and dissolution of carbides. We would do that in the carbon model, and then we would have that as a separate carbon profile going into quench compared to after carburization. Hopefully that answered your question. If you, again, have more questions, go ahead and send us an email here. We'd love to answer them for you at support Dante Solutions and our website as well. Thank you.